All right. So Peter Chave is our from Cisco is graciously agreed to discuss adaptive bitrate coding. You know, it's no longer the time of sitting in front of one television or monitor watching Dan Rather at 6 o'clock. It's anytime and anywhere, and how can you do it effectively and reliably? So, without any further ado, Peter.
Thank you very much.
Thank you.
Thank you, everybody. So what I'd like to do in this presentation is really go under the hood and kind of explain some of the kind of fundamentals of the technology. This morning you heard some of the previous panels talk about ABR technology. They talked about chunked streaming. I'm going to kind of go back a couple of steps and try and explain how we got here. So how did we get to ABR from where we were? And bear in mind, this has all happened in maybe just 2 or 3 years. This is, you know, the industry is turning faster and faster. I mean, historically, YouTube didn't exist 7 years ago. You know, that's just how quick things are. You know, and YouTube's just ubiquitous now. So things are changing very, very quickly. And what's enabling people to be able to watch live, continuously flowing video on devices all over the place is, you know, has really come from a lot of different technologies combining and a lot of best practices being put together to make this actually work. Because, you know, if you look back where we were, there are various live streaming technologies out there in the past. You think of Real Networks, Move Networks, Microsoft had their own variations of this. But it all required something complex, like a special client to be installed. It only worked on a certain device. It required a very dedicated server. It required a special connection, used dedicated ports. Very complicated stateless protocol. But to be able to drive the growth that we're getting to now, the technology had to simplify. We had to get to something a bit easier to manage, a bit that would traverse networks a lot easier, and would be able to enable these kind of flows to happen. Because without that simplicity, or trying to bring some of these things together and try and boil it down, we never would be able to support the growth rate that we're experiencing now. And this will all change again. That's the only thing I can tell you. This is just where we are today, so I'd like to explain that. So, to explain how we got to ABR, I'm going to take a step back and talk about progressive download. So if you're familiar with HTTP is the common way of moving any files from a web server to a web client. What's great about it? What's great about HTTP is all of the web guys for moving text and pictures and audio and everything around across the web used the same single port and would move files in small pieces. So they would download the pictures, the web page, and all these things as elements as lots and lots and lots of small pieces through the network. So the internet and the internet delivery mechanism optimized to moving these small chunks around. Video, traditionally, is great big files. Anything more than 30 seconds is probably multiple megabits. So what the first kind of video players did was to try and solve this problem was you could basically what we call progressive download, which is you start playing the video before you've got the whole file. Not like, you know, download where you would literally download the file and then start watching it, because once you've downloaded the whole thing, it's going to play back nice and smoothly. You're not going to have any pauses. You can seek around in the file. You can pause. You can stop. What progressive download did was basically, okay, I go to a website. I want to watch a video, but before I don't have to wait for the whole 2-hour movie to download. It would basically, when I got a certain amount of that file downloaded, the player would actually start playing it. So one of the reasons these other non-HTTP based video delivery platforms didn't grow as quickly or didn't get as fast, didn't deploy as fast, is because they were a different service. The CDN providers and the service providers had to make special provision for them. They had to put special things into the firewall. They had to deploy their own special caching nodes. They had to deploy another system. And there was one for each one, so they're all different. Web services, HTTP, has been growing exponentially. And so these servers are traditionally cheaper to manage and maintain than other CDNs. And so if you could make the media flow over an HTTP connection rather than over one of these proprietary systems, you could ride that same cost curve. Again, people have firewalls in their homes. They have wireless access routers. They have these which implement a NAT or a PAT table. You have networks with inside companies that have very strict firewalls and everything. The one thing that gets through everything is web traffic. So if we let the video ride over the web traffic over the web port, we can solve a lot of those fundamental transport connectivity issues. We're not trying to solve some of the other, I'm going to talk about the other problems that we've created for ourselves now that we have smooth flow, free-flowing video. We're trying to get that content just trying to solve the basic transport problem. Again, HTTP-based delivered media doesn't have the same, you don't have to have special proxies or special caches, as I mentioned, so it can just go through a traditional web cache. And it's much easier to move that data around. So the bottom line I want to get to here is it was easier to change the video to the web than to change the web to allow video. You know. So this is how progressive download works. What happens is, and this is, if you ever watch YouTube, you know, when you go and watch a video, I mean, it's basically encoded at one format because most of it's user generated. They've started to do a couple of other different rates now. You can get a high quality version. But what happens is when you go to the page, you'll see down the bar, that red line starts scrolling, you know, the gray bar starts running across as your red line starts chasing it, basically. And that's the progressive download occurring. So the whole video file is being downloaded into your browser cache, and that gray bar races along the screen, hopefully faster than the playback bar chases it. But what happens is if the red bar catches the gray bar, it pauses and it buffers. So you don't have a continuously free-flowing video. But 7 years ago, you know, a lot of people were still on 56K modems. DSL and, you know, less so in the US theater, but, you know, where I'm in Europe, you know, high-speed broadband access wasn't as ubiquitous as it is today. So, you know, a friend of mine, as soon as he came to my house in the US, and I've got a very fast 50 megabit, you know, high-speed connection, as soon as he wanted to watch a YouTube video, he'd pause immediately. He goes, oh, I'll wait for it to buffer. I was like, oh, my house has already buffered. But, you know, he was used to that, you know, oh, I'll wait for it to buffer, so at least it'll you know, the video will run smoothly. So what's happening with a progressive download is the web server is sending a request, and what happens is as the buffer cache fills up, when it gets to that minimum point, it's usually like, you know, 10, 15 seconds in, the player will start playing the video, and in the background it's pulling in the chunks, trying to fill up the buffer to keep ahead of the playback. So, but that was the, and what the HTTP protocol supports is a thing called byte range request. So basically you can say, give me from byte 1 megabit to 2 megabit in the file, rather than send it everything from starting at the beginning of the file. And that gives you the ability to seek, because you literally can drag the bar up to halfway through it. It says, oh, okay, give me part of the file that's halfway through the file. It's a very crude mechanism, but it basically enabled fairly good video. You know, it wasn't perfect. And as long as your connection is faster than the content, you would get a free, you know, continuously flowing video. The problem with that, we can say this, is you do have to wait for that buffering period. And depending on the content owner has a problem because they have to work out what bitrate should I author it at. And they really have to go for a kind of lowest common denominator. What's the lowest kind of user we want to try and support to get a reasonable experience? So, I mean, YouTube aims right now at about 360 progressive or 480 progressive. So, I mean, they're, you know, getting up towards traditional SD resolutions now, but still, they're trying to aim at a resolution where most people are going to get a good experience. People on very low-end devices are going to have to wait some buffering time, or they're going to have to put up with pausing. So here's a quick example of, you know, we wait, the file buffers, if this automatically runs. And then once we've got enough in the cache, we start playing. If the network, for some reason, or the device hits a glitch, we've stopped, we caught up to our bar, again, we have to wait for it to buffer. The video doesn't flow continuously. For VOD, you know, you can kind of put it, that's not too bad. For live events, this is a real problem. So, and to give it its full name is, you know, HTTP adaptive bitrate streaming. A lot of people call it ABR encoding. Literally, this was bringing together the concepts from progressive download with concepts from streaming, which had been tried and tested in, you know, Flash have a system out there, Adobe had a system, Move, Real Networks, Microsoft, everyone had different streaming, but again, it required these proprietary underlying protocols and some kind of very clever, you know, servers to manage all of this. So we get to combining some of those techniques with progressive download, we get to HTTP streaming. So we're trying to solve the transport problem. So in a traditional streaming, for instance, you know, RTSP packets to a Flash client, you basically have a very stateful protocol. The client and the server are very tightly in sync, and lots of little small packets are being sent. Each one's a very small chunk of data, and it's very carefully managed between the two. In adaptive streaming, we have this concept where we create on the server lots of different bit rates, but they're all perfectly synchronized with each other. Each of these 2 to 10 second chunks can be interchanged with each other. So you can start on one chunk and then move to another chunk, and the boundary points between the two chunks are exactly in synchronization. That's the clever part of the ABR encoder. What it means is now each one of these chunks is just a traditional file download. So rather than being a proprietary protocol, each chunk can be done through an HTTP GET. So what happens is the client will start, let's get to the client starts by picking usually the lowest bit rate, or at least one of the lower bit rates, because it can get it very quickly. That means you don't have to wait for the buffering, because it downloads as fast as it can. And if you ever watch content through YouTube, through Hulu, or through Netflix, or any of the other kind of over-the-top type providers, you'll notice when it starts off, it's fairly grainy and chunky, and then it suddenly clears up about 2 to 10 seconds later. That's because the first chunks they're sending you are very quick. I notice this a lot on one of the Viacom shows, actually, on the Daily Show, because the beginning's a very fast-moving graphic sequence, and that always looks kind of slushy until it kind of jumps to it actually gets into the show. And you see that because that very first chunk's coming out very fast. Now there's optimizations in there. The buffering requirements can be solved because what happens is if you start loading chunks into the buffer, you're filling up your video buffer of what you're going to display. If you start finding that you're not getting the pieces as fast as you were, you can move down a bit rate. You can go to something slower. So at least you can keep the video flowing, and that's the whole aim here, is to have a consistent playback. And this really does move the burden from the content authorer to the client as to what quality presentation it's going to present. You don't have to try and guess or pick that lowest common denominator format anymore. You don't have to think, well, it might be, I'll go for 480, and that will put some people off on the mobile devices, but people on the TV, on the PCs will have a good experience, and the people on the big screen TVs, it's going to look kind of like SD video. Now the client's really in control of of understanding its own capabilities and understanding the network capabilities to give the optimum presentation. What happens when something goes wrong on the network, and what happens if the device displaying it runs out of horsepower? And it really does get us to this any device, anywhere, anytime paradigm. That's really one of these fundamental technologies. And you see a lot of these other, especially a lot of the other providers collapsing in on this as being the way to solve that problem, because it has all of these advantages in the transport layer. How does it actually work? The client really becomes the key entity. So it's monitoring its own buffer, knowing how many chunks it needs to get in. It monitors how much resources it has itself, how much, it knows what its screen's capable of displaying. There's no point on the iPhone, well, an older iPhone anyway, downloading a 1080p picture. I'm sure the newer iPhone will be at that kind of risk. But the screen real estate size is a certain value. There's no point downloading a picture that's bigger than the real estate. So it knows how big the screen is, and it knows how good its current connection is, because I'll walk through this in a second. It's obviously, it can time how long it took to receive the last chunk. It also there's this concept called fragments and manifest, and in MPEG-Dash they become kind of harmonized, because this is where I'll get into the complexities of ABR, where having solved the smooth flowing video, and no pun intended for Microsoft there, and solved the transport issue and made the video run consistently, now we have everybody else in the game having their own different versions of how that should be implemented, and that's what I'll talk about in a second. So you have a manifest file, however that's implemented, and you have the fragments. So it manages keeping track of the fragments, keeping track of the connections, and that will get us into the CDN discussion at the end, what that challenges that poses for a CDN. And lastly, okay, and the client does the adaptation. So I have a quick, this is a screenshot from a Microsoft Smooth player, and you can see the bit rate over different time is changing. This is just a typical simulation. I'll show you a kind of a walkthrough of it here. So the first thing the client does is it requests the manifest file. The manifest is just a list. It could be a text file, an XML file, or whatever the format of that particular standard, particular protocol uses. But in that file, it just has a list of locations on the web server of where all of the chunks are for each time. Now, it may be done as a manifest of manifests, one manifest for each one, or one manifest that describes all of them. Again, that's the implementation complexity. But basically, essentially it's a list of web pointers saying, okay, The 0 to 2 second file can be found here, here, and here. The 2 second to 4 second file can be found here, here, and here. So it's just a list of URLs. So the first thing the client does is it grabs, let's grab the 300 kilobit chunk first, downloads that into the thing. As it downloads it, it goes, oh, I got that 300 kilobit file in like less than a second. We can go up a bit rate, because as long as I'm getting it in less than 2 seconds, we can stream at that rate. So the next time, it goes, so it goes, I'll move up a rate. I get the 700 kilobit rate. Oh, I got that in less than a second too. Awesome. Let's go up to the 2.4 megabit rate. That's fantastic. Okay, I got that. Oh, hang on, that took 3 seconds. That's because there was a glitch on the network. Oh, go back down to the 1.5. Okay, we got that in 1.5 seconds. Oh, great. And then so over time, as the network changes, as the bitrate changes are available to the client, or it turns out that my son starts streaming on his iPad and it starts bogging down my router and bogging down the internet connection. As more connections come on, or just the macroscopic environment changes around that particular client, the network adapts, and this is really what the fundamental of ABR technology is. So this is awesome. Oh, that's great. We're using simple web objects which traverse firewalls. We've got a system that adapts to the way that the client operates, the way the network operates. We've solved a lot of great problems. This is a typical end-to-end system today. So you have all of the content being produced. You have a device that does this encoding that creates all these different versions. And then you have a thing which does the encapsulation. So this actually puts a wrap around those chunks, the segments, and creates that manifest file. Now, there's Smooth, Flash, Move, Apple. They all have their own version of this. And they all do the wrapping and the chunking differently. They push that file out to a origin server, which is a web server. And that origin server has to manage all of those pieces and push it onto the CDN and send that out to the end devices. So the challenge, and I think David from Viacom touched on this first thing in the morning, was the service providers and the service providers, i.e. the people delivering the content to the last mile to the home, and the content owners, the people producing it over here, are currently in a debate. They're trying to work out where the line gets drawn, right? Does the content owner go all the way to the edge and say, okay, we're going to deliver our content direct to the home, so truly over the top? Or does the service provider say, well, no, just give us a mezzanine version, we'll create that content, and then we'll push it through our CDN? Because they both have a challenge to solve. The service provider, if it's a pure over-the-top play, say it's Netflix running over Comcast, right? Comcast is just the pipe. They have no idea what somebody's sending over the top. They have no idea what that content is. So if they knew what the content is, maybe they could help recommendations for other live content, other stuff in their catalog. And they could also address demand on the network and help, rather than just saying, hey, we need like X gigabits of capacity on this link. They could say, well, actually, if we put a cache node down there for Netflix, this would really help us, because it turns out it's all Netflix traffic. On the flip side, the content owners have a problem, because if they literally just rely on the service provider to just push the bits through, they have no idea what they're doing. They could be throttling them down. There could be really bad problems on the network. They have no idea they have very little visibility of the final product. They don't know how well it's going to perform. All they may get back is saying, okay, we know that they took the 400 kilobit stream. Well, they don't know the reason they took the 400 kilobit stream is because they're running on like an Apple iPhone from 1 or something, or they were using just because this connection was very contended. So there's definitely, where the line gets drawn is one of the big debates. And so there's definitely a place where both parties can get what they want out of this through some kind of collaboration or some kind of overlap. And we're starting to see that happen. So that's definitely one of the things we're seeing between the broadcast and content owner world and the service provider delivery spaces. So why do they need to solve the problem? Well, I think the statistics somebody showed earlier is they expect in a couple of years mobile video traffic to be over 80% of all web traffic. The numbers I have is that we're already at 92% of all traffic on the web is video. And that's getting worse. And it's not just the percentage of traffic that's video, it's the, so this is video, this is everything else. And we anticipate the video will outpace all the other traffic at more than three times that. And what's the bigger challenge is that the mobile video traffic will be going up almost 12 times because as more people, as these devices are so ubiquitous and people want to consume content on them. Yeah, so the problem of how do we solve that challenge for the network and the delivery and who owns and where the line is drawn between the service provider and the content owner has to be solved simply because it's a numbers game. We've managed to solve the, making a free-flowing, continuous video that traverses networks easily. Now we've created a new problem for ourselves where this stuff's, the reason we had to solve that problem is just because we're on this curve of people consuming more content, more places. It's just a pure numbers game. So, I'm going to talk to the big three. There's other players in here, but between HSS, or smooth streaming, as it's known from Microsoft, HLS, or HTTP live streaming from Apple, and HDS, there's a theme going on here, I'll just call it HXS, from Adobe. They all agreed that HTTP was the transport protocol. Solve that one. Okay, fragment size. 2 seconds, 10 seconds variable. Okay, we can get them to try and agree on that. We can change that. Number of TCP connections needed. Okay, not too bad. The one thing they really did agree on was the codec. It was H2.64. A lot of the native devices have that built in. Codecs and that, I'm not so concerned how quickly they evolve because the devices change much quicker than they ever did. The stuff's being replaced on an almost 18-month cycle now. I mean, who has an iPhone 2? iPhone 3? Okay, it was at least an iPhone 4 or better, right? If not, this stuff gets replaced very, very quickly now. So the codec, we have agreed on MPEG-4 for now. The audio has pretty much coalesced on Advanced Audio Codec, or AAC. Now, whether it's LC or HE really depends on the final device. But you see, everything else is kind of a mess. DRM particularly, Microsoft have PlayReady. HLS don't really have a DRM. They allow AES encryption. You can wrap HLS with PlayReady in a kind of convoluted client architecture. And Adobe has Adobe Access, which they really haven't kind of defined yet. So all of this stuff is in huge flux. And this chart is at least 3 months old, so it's probably completely out of date already because this stuff is changing so fast. At least the way, but that's kind of just showing you that there's a lot of different, between the different major organizations supporting this, we've managed to solve some of the fundamental problems, but we're now got to deal with the next layer of complexity on top. So MPEG- is an attempt to try and solve this layer of complexity by trying to force a commonality or a common set of things. But again, until either one of these three guys moves to it wholesale and says that's what we're going to be totally Dash compliant and that's the way we'll go forward, or one of the service providers or one of the big content owners pushes it as being you shall support this for all streaming formats. That's kind of the, we're waiting, the industry's in that kind of mode right now. If we look at other stuff, and this is really, really important to us, things like multilingual support, ad insertion, and particularly captions, because now it's been mandated by the FCC, we have to solve this. Again, very different implementations. Again, we hope this converges, and that's what we're trying to push folks to think about, and that's what the industry is trying to push folks to do. Certainly, from SEMPTI and from ISO and from Cable Labs and from a lot of the other forums, they're trying to work out how all this comes together. There's a lot of work, especially where the money is, ad insertion. That's where a lot of the money comes from. We want to get that right. So Cable Labs has a really good group right now working on specs for that. Captions. SEMPTI's pushing something for this. We're really trying to get these coalesced. But you see, there's lots of different implementations in each of these different formats. So, how can we address that divergence? How can we try and solve the problem we have today and be prepared for stuff to either change again, for new things to evolve, or for new standards like Dash to come out and then be mandated and push us back into this? So, this kind of shows you the flow of, traditional pizza box type encoders. You've got a pre-segmented and a continuous fragmented for both Smooth and HLS, which then go to separate. A Microsoft only works with a Microsoft ISS server, of course. HLS works with any web server, because it's literally just pure files. But you have to keep track of a lot of very small objects, so that's a different challenge. That then has to be pushed out to the CDN through the network. So our vision is that you basically try and, if you look down the chain, what you start with one stream, okay? You then end up with n bit rates. So Viacom said 8, that's pretty much standard, 8 bit rates. 4 for SD, 8 for HD, that's pretty standard. So you end up with 8 streams. Now we have the different encapsulations. If we want to support all 3 of the big ones, Apple, Microsoft, and Adobe, so that's 8 times 3, 24. We've now got 24 streams coming out here, okay? Now we need to encrypt it, okay? Assuming each one has only one DRM, maybe you can't. In a multi-delivery world, you might be delivering content to lots of different devices that have different DRM capabilities. You have another multiplying factor, so you've got 24 by the DRM count. So what you end up on the origin server is a ton of files, and a lot of maybe unused storage. On the origin server itself, so the origin server is a web server. It could be ISS, Apache. It needs some of the different distributions, namely Smooth and Adobe need a helper. This is a plug-in to the server that actually kind of reads the files and helps fragment them or chunk them out to the clients. So you need this helper or fragmenter or function. Like Smooth, it stores it as one big file. And then the web server, when you send in a request, says send me 2 to 4 seconds rather than send me 1 meg to 2 meg. It chunks out just that piece of the file and sends it to them. In HLS, it's not. You basically have one file for 0 to 10 seconds, 11 to 20 seconds, 21 to 30 seconds as separate files. So it just does it by a pure get. But what you end up with is, say, for a half-hour movie, it's like thousands of files. And then you multiply that by the number of bit rates. So you have 8 times the thousands of files. So you end up with a lot of small files. Versus Smooth, you end up with just 8 files, but they're really, really big. So it's just different, different horses, different causes. But again, you need a function to do that. And at the end of that, that feeds into your CDN, which what we're trying to do with all of these very clever computers is emulate what satellite's done for years, which is be able to send one signal to 1,000 different places. What a CDN does that across an IP network in a very on-demand, to the end customer. What if you take all of that pre-functionality and make it a single platform? So make transcode, encapsulation, encrypt, origin, and helper all on one box, or at least all on one software system. And then you can basically take them apart, and the concept we have is we call a virtual origin, which is where you basically take everything. We separate out the pure encode function, because we see that can be very easily offloaded to either hardware or to other appliances. And then you take all of the other functions and make them individual instantiations where you can scale them individually. And you can distribute them. So you can move, I think somebody mentioned this morning, I think Peter, it was you mentioned about moving the fragmentation out to the edge or moving the encapsulation out to the edge. So you don't have to do through the CDN. If you've only got, at one edge of you've only got iPhone devices, why send HLS all the way through the network? Only send HLS, put the fragmenter out at the edge and do the fragmentation for HLS right at that edge. So that's what we call the virtual origin concept, where you split these up and try and spread them out. So we start to talk about things like cloud DVR, and certainly all of the MSOs that I talk to, that's one of the big pushes, is to try and move to a cloud DVR functionality, simply because they don't want to have to maintain these set-top boxes in the home that cost a lot of money. Bad for me as on the other side of the business, but they want to be able to offer this as a function. By having a single architecture for all of this functionality, it allows you to split it up and spread it out, which allows some of these other architectures to evolve and come out of it. It also allows a lot more resiliency in the system. And the most important thing is, really, as the different vendors of the streaming technology change the standards, they come out with a new version of X, Y, and Z, it gives a lot of agility because you're only replacing just that one function, now not a whole machine or a whole stack each time. It also, as things like ultraviolet and MPEG-Dash, and how those things play, and whether they become more popular or whether they become prevalent or whether they take over, having this kind of architecture where these functions are split out allows you to swap out just those components very, very quickly. So you can evolve to new standards much faster than if you've got all of that functionality, for instance, in the encoder, where the encoder box that you buy spits out pre-encapsulated Apple, Microsoft, and Adobe. If you have all that functionality separated out as separate software modules, which you can then run on a cloud system or run on your own server system, you can then separate that functionality and be much more agile to the changes. What does a virtual origin give you? It gives you the ability to do things like just-in-time processing, which means you store all of the chunks that you created from the encoder, but you don't create the manifests, you don't create the fragmented wrapped versions until you actually need them. So this is what really enables things like Cloud DVR and these other kind of functionalities. I'm running out of time, so I'm just going to quickly skip to this one here. So what you can do is you get the the live or the VOD file that's just been encoded to MPEG-4. That's all we've done, MPEG-4 and AAC. Didn't do anything else to it. But they're adaptively encoded, which means they've got the markers in there. We can record that, and then as we only had to record 1 copy, not 24 copies. Okay. Oh no, sorry, 8 copies, not 24 copies. Now, as a client requests them, we can literally just, with a just-in-time processor, we can fragment them for the device that's requesting it, and we can generate the manifest right at that moment. If somebody else requests the same one, they just get a copy that's already been created, but we are only creating copies as needed. So this gives a lot of savings in terms of storage and a lot of processing requirements. You're not having to build for the worst case, you're only building for demand now.
Is this different than what's being done today?
No, so this is different than what's being done in most networks today. This is starting to happen in, there's a couple of MSOs that are starting to build this, and we'll be launching live product on this probably in October, on at least this system here. So yeah, what's done today is they're literally, if we go back to that diagram, is they're creating, this one's actually, let's go back one more, is at the edge of the network they're filling up the origin servers with all the different possible versions. And then only as it's requested is it being served. Well, one of the reasons you want to try and break apart the traditional boxes that were drawn around these functions and redraw the boxes is if you can separate the transcode, you can do that on, say, a very high, ASIC-based, high-performing appliance. Because transcode is a hard task, so you can make some savings there if you want to. If you separate these functions out, then you can do them where you need to, and you can do them on demand. Because, I mean, this is the reason the boxes are drawn this way. This is typically an ABR appliance today. That's what the box looks like inside. Now, what's happening, and this is what an origin server looks like. If we separate the boxes out, and this is what's happening, this is products that are being sold today, is redrawing that as separate boxes, and we call them under a banner, we call it our virtual origin server. So that was the why we're trying to allow. Now we've solved the fundamental problems. How can we help address some of the other divergence going on and address some of the other changes that could be happening, and some of the benefits that if you move to that kind of architecture, some of these other newer things that people want to do can be done. Just want to spend 5 minutes, if I've got 5 more minutes, to talk about the challenges that ABR loads onto a CDN. So the CDN is traditionally an architecture that moves content very efficiently from one place to multiple points. And just to show you some of the complexities of this, I'll skip some of the words, but if you're doing like a single file download, you have the file, and so this is a progressive download. It's one TCP connection, and it's one transaction. So it's, we start it up, sending chunks, we ACK, we're done, and the connection's finished. If you're sending an HLS file, you have to send, the N profiles, the N times the number of segments you need for the length of the video, plus the manifest that support. You have one manifest that points to where all the other manifests are, and then one manifest per profile. So you have one manifest for all the sequences, and one manifest that points to all the profiles for all the sequences. So what you end up with is one TCP connection every 5 to 10 seconds, and it's doing about one transaction every 5 to 10 seconds, just based on the number of chunks. So you've got a lot more TCP connections going on, and you need to have them every 10 seconds, not just once for the life of the content. With Smooth, you actually have two connections going on, because they're actually overlapping the two sends, because if they need to get a different chunk, they'll get it on a, so you actually end up with 2 TCP connections, and Smooth works on a 2-second segment. So you end up with 2 transactions per second, 2 TCP connections and 2 transactions. The last example is Move, which is 3 to 5 TCP connections, and it's 2 to 3 per second, and it's 3 transactions every 2 seconds. So what you've moved from is a very, if I say a half-hour movie, I had 1 connection, 1 transaction, and I'm done, to hundreds, thousands, and multiple thousands of connections and transactions occurring. So whereas an old progressive download, say a single movie, I end up with, for each of my different bit rates, each of my fragments, I end up with lots and lots of objects that need to be moved through the system. So the CDN from being loaded one way is now being loaded with a totally different type of traffic. So it now has to be very, very agile to these small fragments and very short-lived TCP connections, which That's what websites are very good at, traditionally. That's one of the reasons we moved to HTTP. But now we're talking about a lot more traffic. A typical website maybe loads in less than 100K. We're talking about megabytes of traffic over these transactions. So it's like there's a lot of connections, a lot of objects, there's a very continuous traffic. So the challenge for the CDN guys is making optimizations to handle lots and lots of TCP connections, lots and lots of HTTP transactions, and doing things like some of the enhancements you can do is like request bundling. If you've got 10 clients from the same area all requesting the same piece of content, well, send that request once back up the network. Don't send 10 connections all the way up, all the way back to the origin server. So being able to do these kind of things, especially for live content and content's coming out. Optimizing for small objects, and changing what a small object is. Small objects used to be very small. Small objects are getting bigger. But if it's a very small object, short-lived thing, you may not want to cache everything onto the disk. You may want to just keep that in RAM, because maybe this one client requested the 300 kilobit connection, everyone else is on the 3 megabit connection. Well, that 300 kilobit is probably not going to live very long, because not many people are going to want it, because it just happened to be this guy, he was multitasking on his Android, and he was doing something else when it came in, and so the CPU was running slower, and it's like, oh, give me the lower bit rate. So again, small objects to memory, delayed write to disk, large objects, keep continuing to cache them, because that's the efficiency of the CDN. Protecting the content that's coming down the CDN, because when you have multiple clients connecting to this content, you really want to protect your CDN from being people kind of bypassing some of the CDN functionality and kind of going deeper back to the origin server. So you want to keep them at the edge of the network. So having things like content signing and access authentication on the URL. So people aren't ever connecting to a hard link. It's always soft links further down the network. And then adding the kind of availability, the kind of intelligence into the CDN such that it understands the behavior of ABR content and understands the different clients and the different devices and the different structures we have today, how they interact with the CDN and how they're going to send requests, so that you can basically do much better efficiencies in the way you collect those requests together and send them up. And if you start seeing a stream run, you may start predictably getting other pieces and understanding how that's going to flow. And analytics, I know I'm way over time, so I appreciate your patience. Thank you very much.